So, good morning, guys. Good morning to all these brave souls that have joined me at 9 a.m. to hear me talk about TypeScript for 60 minutes. Not sure I would have done this. I want to also thank the production for a really, really impressive production. You can really feel that everything has been thought through. So yeah, just a really impressive event. We are going to be talking about one of my favorite subjects today. So I've been speaking about TypeScript in meetups, in conferences, in podcasts for the past few years. So this past year has been extra exciting for TypeScript enthusiasts with a lot of really exciting innovation that's happening in the TypeScript ecosystem. Run, run, run. We haven't started yet. So it's going to be quite a journey, okay? So we're going to start this talk in just like discussing the world of the problem of like, why does TypeScript exist? What does it solve? Then we're going to talk about what does it not solve and how do we solve what TypeScript doesn't solve. And we are going to do a small deep diving to see how does the TypeScript compiler really work under the hood. And last but not least, we are going to finish this session with talking about the future of TypeScript, which is very, very exciting and innovative. So my name's Ariel. I'm a full-stack developer at Factify. At Factify, we aim to end paperwork. If anybody has more questions about that, please don't hesitate to ask me later. I'm a mother of Ginger. This is Ginger. She's a backend developer. And besides that, I'm a public speaker. I'm a TypeScript enthusiast. And let's go. Raise your hands if you use TypeScript. Cool. Wow, you don't write in TypeScript and you're here. Kudos. So I'm going to tell you a secret. Every conference I went to and I asked this question, the statistics have kind of been the same. It's become industry standard. And for a good reason, right? Like, we prefer to fail during compile time than to discover bugs during runtime. And type safety is really, it's just a key ingredient when we want to have robust applications. And TypeScript really does give us type safety. But I think it's also really important to understand where does TypeScript not protect us. And I'm going to start with a harsh statement. And I'm going to say that if you're doing type validation with TypeScript alone, then you're either lying or you're working too hard. But to explain myself, and why do I say this, I want us to go a bit deeper. And let's just talk about the concept of just a TypeScript file. When I look at a TypeScript file, what can I find in any TypeScript file? I can have functions and objects and variables. I would have classes, enums, types, interfaces. And we're very much accustomed as developers for all of these creatures to be living together happily in the same file. And the harsh truth behind this is that this is syntactic sugar that hides something less sweet. So as a matter of fact, when we are working in a TypeScript file, we are basically living in two spaces at the same time. Okay, so the first space is the type space, and the second space is the value space. So the value space is everything concerning data, data manipulation, and the type space is everything concerning context. Now, these two spaces do meet in two very specific places, which are enums and classes. And if we give this an extra thought, enums and classes are data with context. And like I'm telling you, listen, you're living in two spaces at once, and you're thinking to yourself, what did I drink last night? And a really, really easy way to prove that I'm sober and you are living in two spaces at the same time is this very simple proof. We can define a type and a constant with the exact same name in the same file, and this works. Why does this work? Because these creatures don't really live in the same space. And this is what I like to call the development matrix. Because when we are developing, we are in this matrix that we think that all of these things live together happily. But the truth behind this is that this is a matrix, and in the real life, which is known as JavaScript or runtime, the types don't exist. JavaScript is what's eventually going to be executed in runtime. So the runtime universe is actually half of the world that we're used to seeing. And this is really quite confusing, I think, especially for junior developers, but even later on, like it's quite confusing that what you work on as a developer and what eventually runs are completely different. So how is it possible? Like, how can we write the code in one universe, but eventually something completely different is going to run at the end of the line? And it's possible thanks to a process that's called transpilation. And transpilation is a combination of transform and compile. So if compilation is taking a source code and processing it into machine code, bytecode, transpilation is taking a source code and processing it into another source code. So in our case, TypeScript to JavaScript. So we're going to do a small deep dive and understanding how does the TypeScript compiler work under the hood. So hold on tight. So the TypeScript compiler works in 4 steps. It actually works in 5. Like parsing actually has a pre-step of scanning. But just for this case of this talk, we're going to treat it as 4 steps. So parsing, binding, checking, and emitting. We're going to do this small experience on this really cute 2-liner and see how horrible it is just to type check this tiny thing, just to start wrapping our heads around what really type checking demands. So the first step, parsing. Parsing receives as an input a blob, so text, code, and on the output, it parses it into a tree. So when we parse the first step parses our code into a data structure called an AST. So AST stands for an abstract syntax tree. It's a data structure that represents a program of code. It's used by most compilers, not all, but most. And this is not really the full AST. So like the real AST actually has a lot more nodes than these. This is a slim representation of it. That I think that the slim representation is better for having a better solid understanding of what the AST is actually about. So we're going to be using this slim representation of it. So we had a blob, and now we have a tree. We have an AST. And now we are at the second step, which is binding. So binding is basically creating more links on the AST that would be used later for type checking. So for example, when we bind this tree, the getMessage function invocation is actually bound to the getMessage function declaration. The input message that is returned is bound to the input message that was received as an argument. So binding is basically adding some extra links on the tree that would be used later on when we type check. And type checking. Many people treat this like it's some sort of magic. Like, I hear a lot of people like, OK, yeah, so it's just the type checking. It's actually a state of the art. It's a really, really, really complex mechanism that demands a lot. So we're going to see how much it demands in this really tiny example. We're going to look at type checking from 2 aspects. So the first aspect is, like, I want to ask the TypeScript compiler a yes or no question. I love TypeScript. Is it a valid argument for the getMessage function? Can I pass it on to the getMessage function, yes or no? And in order to answer that question, the TypeScript compiler is basically going to be traversing on this tree. So it's important to understand that when we check, we actually don't mutate anything. It's just traversing. So we want to know, is I love TypeScript a valid argument? So I love TypeScript is an argument of the getMessage function that's bound to its declaration, that got an input message as an argument, which has a type definition of a string. I love TypeScript does satisfy the constraints of a string. So the answer for my question is yes, it's a valid argument. But the more complicated question we can ask, and really I would say the most complex and interesting mechanism in the TypeScript type checker is inferring. So I could also be asking questions like, what type is this element? So like when you hover over anything in your TypeScript file and you think it's like, or JavaScript file, and you think it's like magic that you see that it's of type string, you actually have trillions of tree traversals going back in the background of your IDE in a node process that's always running, that's basically the language server. So if I want to ask like a more complex question, I want to ask what type is message 1? And it's quite interesting because we never explicitly said what type is it. It's actually inferred. So inference is actually also a traversal on this graph. So when we want to ask what type is message 1, when we hover it over it on the IDE, what basically happens is that we travel again. So message 1 is the return of the get message function invocation. It's bound to the declaration. It returns an input message that's bound to the argument, which is a type of string. I know this was hard. It was hard for me too. It's just important for us to understand how hard was it to do a simple two-liner for the second part of this talk. So the last part of what the TypeScript compiler does is the emitting phase. As a matter of fact, emitting actually only happens when we build our code. So like as I said, when we're working on our IDE, our code is actually constantly parsed, binded, and checked all the time. Emitting is something that happens when we run build, okay, when we build our code. So in the emitting phase, we get as an input an AST, and the output is JavaScript files. Could be TypeScript declaration files, could be source maps, but this is kind of like a reverse parsing, okay? So we go to tree and we create code. And so what happens when we emit JavaScript is basically all of the type nodes are omitted, and then it's kind of like a reverse parsing, so the tree turns into code. And a lot of people I hear treat this step as type stripping, and I really strongly disagree with that terminology, because actually a lot more than type stripping happens in this step. This is also the step where transformations happen. So let's say that I want to support ES5. In ES5, I didn't have the const keyword yet, for example, so this is also the step where transformations happen, where, like, for example, const would turn into a var, and so on. We kind of know how does the TypeScript compiler works, or at least the steps that it works in, because we really did a single file example, and the moment you have more than a single file, that's where things get a lot more complicated. We're not going to get into that in this talk, but it's important to know this. I'm going to be referencing things from this next on in the talk, but I want to go back to my harsh statement from a year ago, that if you're validating your types with TypeScript alone, you're either lying or working too hard. What do I mean when I say lying? This is lying, for example. I have this person type. I have this getPersonAddress function. I'm making an API call, and then I lie. Why is this a lie? Because we know that in runtime, we're not going to have any types, right? And in dev time, I am making an assumption over runtime. But if in runtime, this person would not even have an address property, this young fellow would be a runtime error. And we don't like runtime errors, right? We all raised your hands that you use TypeScript. This is like exactly missing the point of everything that we're trying to do. So an alternative when you're only using TypeScript is to work too hard. So how would working too hard look like? Kind of like this. So I could type check it, could do some type narrowing. I could see that this person has an address property, that this address property is an object, that this has a treat property, that is a string, and I got tired from just saying out that validation. And besides like me wanting to be lazy, this is even a bad architecture, because I don't have a single source of truth. If I make further alternations to this person type, nothing would force me to keep on updating my runtime validation. And this is not good for us. So there are a few, this is a solved problem, okay? We're going to talk about the industry standard for dealing with this problem of data that arrives in runtime, and we would have to manage the type safety of it. So we're going to be talking about Zod, which is really an industry standard by this point. Zod is a TypeScript first schema validation library. I gave a talk about Zod in a conference when it just started gaining a hype. That was around here. We are exponentially growing, also thanks to AI. So a lot of AI SDKs implement Zod for communication between AI agents to make sure that the schema that they return each other is correct. And I think the best way to really like wrap our heads around it is through code. So let's write some code. I might have some old stuff. So let's start. We're gonna do this step by step. Okay, so we're gonna start with just a simple intro to Zod. I'm gonna do it as a JavaScript file. So I'm gonna start with just import Z from Zod. If anybody doesn't know Zod, so this is the syntax. I call it the magical Z object. I'm gonna enlarge it. Wait, let's see. Does everybody see? Good. So I'm going to be using the magical Z object. The whole API of Zod is encapsulated with this letter. So we're going to start by like solving the problem that we just saw. Like, let's try to define a schema for a person that I could check in runtime that a person complies to some contract. So I'm going to be using the magical Z object. I'm going to say that a person is an object, and it has an ID property, which is a string. And it also has a name property that is also a string. Easy. Now, each Zod schema, implements a few parsing methods. So the most basic one is just a parse. So you can see it accepts data that is unknown. So in runtime, it could be accepting unknown data. So let's now pass it something that I know that is wrong. I'm going to pass it a string. And we're going to say that person is the result of this parse, which we know that will fail. So let's run this. Let's open a new terminal. Let's run this. So Zod intro.js. And we got an error. We see invalid input. It expected an object, but it received a string. So far, just like any normal schema validation library. So let's start making it interesting. First thing that's interesting is that if I hover this person, I can see the type inference. We're in a JavaScript file. I just wrote a runtime validation. I wrote a schema, a function, but I have the result inferred very nicely. This is what makes Zod like TypeScript first, and Zod is also a really, really good strategy for projects that are trying to like migrate into TypeScript from JavaScript. So it's a really, really good bridge for going between the two. And it's something that could be, as you can see, I'm in a JavaScript like file. You can just implement it in JavaScript and slowly move into TypeScript using Zod. So the parse method is like the most basic one, and as we see, it throws when it has an error. And like sometimes we would want to throw, but usually we wouldn't really want to throw. We would want to manage it ourselves, like what happens on failure. So this is where safe parse comes in. So safe parse returns this validation result. That validation result is an object that has this success flag. That when success is true, I'm going to see that the validation result is going to have data that is the person type, and the error, if HC, is undefined. And same thing the other way around. Like if I do on the else clause, where I know that success is false, I'm going to see that validation result is going to have an error, which is a Zod error, the same that was thrown before. Now, before we continue, I want to just for a second stop and focus on this pattern, because this seems like it doesn't seem interesting, but this is actually my favorite TypeScript pattern of them all. It's a TypeScript pattern that's called a discriminated union. And I was surprised to see how many people don't know it, or at least some know it but don't know how it's called, but many just don't know it. So let's just stop for 1 second and talk about this awesome pattern. So I'm going to implement the same API that Zod just implemented, the same one that we just saw. So I'm going to implement a safe parse result that's going to be a union of two things. So the first is a successful result. So success is true. And let's say that data in this case is just like, let's say it's a number, and error is going to be undefined. And on the other hand, it's going to be a union of success when it's false. That data is undefined, and error is, let's say, a string. Okay? Now, this allows us to do something very, very cool. So let's have a function that accepts get result. That gets a result that's a safe parse result. And then we're going to see an interesting thing. So if result success is true, like as we saw before, right? We can access result.data. It knows that data is a number, and it knows that error is undefined. Same thing outside that result, when result is, the error is going to be a string. Why do we need this? We need this because of how TypeScript handles unions. Because for us as developers, like the most intuitive thing when we see something like this is that we think, okay, it's either this or that. But actually, for TypeScript, until you prove it otherwise, it's both. So this is, I like to call it Schrödinger's union. When we're not inside the scope that tells us exactly which one of these is something, we're going to see that here, result.data is actually both undefined and a number. I couldn't be performing anything on result.data until I prove that it's a number. So this discriminated union, it's a pattern that basically says that when you're dealing with unions, on each part of the union, you add a discriminant. So a key that doesn't overlap in any part of the union, and then you can help TypeScript do some type narrowing. And this is really, really useful. Like, this is a simple example of a Boolean, but it could have also been, like, for example, a status that could be like idle, loading, error. It could also be, and this is like really useful as well, like, and it could also narrow down even when it's like not a true or false, right? So I could do like result status if it's idle, or else if result.status is error. And what's cool is that TypeScript even knows by itself, like by the end of this last else clause, it already knows that result.error is going to be, it's going to be loading. That it's number, so we see. We're going to see, it already narrowed down, like it knows by itself that by this point it could only be this one. And it's really useful, like for front-end, for example. I love using this with variants. So like when you have a component that in different variants could receive different props. So it's really, really useful. I use it a lot. So, okay, we did a small side quest. Let's go back to talking about Zod. So we saw the most simple API for just like schema validation, but so far, besides like the nice type inference, this is just a normal schema validation library. So let's see how do we make it, what do we need to do to take it beyond the normal. So we're going to turn this JavaScript, bless you. We're going to turn this JavaScript file into a TypeScript file. And then we're going to use Zod's probably coolest feature, which is the following one. I'm going to use Zod's infer method that I'm going to pass on to it the type of the person schema. And what I get here is a type that was generated from my runtime validation. This actually solves the problem that we talked about earlier, that we actually have a single source of truth. My type and my runtime validations are the same one. When I keep updating my runtime validation, my type would keep updating. And this is kind of where Zod like at least led at the beginning, I think. I think that all of the schema validations kind of like leveled up by this point. But Zod has really, really high success rate in also dealing with highly complex schemas and like inferring the right types out of very, very complex ones. We got the basics. Let's go slightly beyond the basics, and let's see how we can use Zod to leverage dealing with environment variables. So in any node, most node projects that I see, and I see the way that environment variables are handled, I hate it. It's disgusting in most cases. So we kind of see like two approaches in most places. It's one out of two that both suck. We're going to see both of them. So let's say that we have a function get connection that gets a URL to the database, and when we want to connect to our database, we get a connection from this get connection, and we want to take the DB URL from our environment variables. So I see one out of two things that I hate. This one I hate, I think, the most. I don't know, I really don't like either approaches. So this is the first approach, this bang operator that basically tells Typescript, I know better. I know I'm going to have that environment variable in runtime. Of course I am. Do you? Do you know that your DevOps is not going to forget it? Do you know that nothing's going to go wrong in deployment? Do you know that you're actually going to have it? I'm not sure about it. And another alternative, which is also quite bad, is in order to not have a type error, is to give it a default value, which is really equally bad. Who knows what's 5432? Postgres. Okay. So both are bad. There is a better way. So we're gonna see how can we leverage Zod to really improve both our runtime safety and our developer experience in one shot. So we're going to start by, of course, implementing Z from Zod. And what we're going to do is we're going to define a schema for our environment variables, which is basically, anyways, a really good practice. Like, obviously, we know in advance how does the schema of our environment variables should look like. And if we don't, then it's a problem as well. We should know it. And it should be unified between different environments. So we are going to define our schema of our end file. As we see, we have like this DB URL. And what we're going to do, you remember when beforehand I said that like many times we would want to handle failure ourselves. We wouldn't want to throw an error. This is actually a case where we do want to throw an error. Like I would expect, like when I start my server, if my environment variables don't apply to the schema I expect, I don't want my server to even start. Not this. I'm going to do process n. And if the environment variables don't match my schema, then I would want to throw an error. I wouldn't want to start my server without all of my environment variables. That's actually what I hate most about this approach. Like, I don't even want to reach this point in the code if I don't have my database URL. So this kind of like solves it to us. We're going to see how does it run, and we can run it in, like, there are really few cool innovations in the Node.js ecosystem that allow me to run this like really easily. So first of all, I can even just like run this environment variables Typescript file. Like I couldn't do this 2 versions before in Node. That I can do, I don't know if you can see it. I can do Node environment variables and just like run a Typescript file with the Node CLI, and it just works from Node 23. And besides, another cool innovation is that I don't need any external libraries now to run like .env files, because directly within the Node CLI, I can say that the env file is .env, and Node just finds my .env file. I don't need to use any external libraries. So we're going to run this, and like we see this experimental warning that type stripping is an experimental feature. So basically, as we said, you remember when we said type stripping, right? So basically what happens here is that Node actually transpiles the TypeScript internally before passing it on to V8. And that's how we don't need to build our code or use like TS Node or to use TSX. But let's try to like just make it fail, just so we see how it looks like when we fail. So we put a number, and now we have an error that DB URL expected a number, but it received the string. So this is nice. Like, I think this is really good practice. We get safety for our environment variables. And that's really important, but we didn't solve this annoying thing yet. Like, we still want to improve this experience. And the way to improve this experience is by using a TypeScript pattern called merging declarations. So there are a few TypeScript entities that are extendable by default. So we're going to declare in the global scope. Okay, and what we're going to do is the following thing. So we're going to start by merging declarations with the Node.js namespace. Okay, so we're going to extend the Node.js namespace. And we merged into the Node.js namespace, and now we're going to do another merging declarations into the process environment interface, which defines the environment variables. And we're going to say that it extends the type of our environment variable schema. Type of environment variable schema. And now what we did is the following thing. I have auto-completion on my process end, on my environment variables. And it's declared in the global scope. Like even if I go here and I do process end, because I declared it in the global scope. Okay, so my whole app could be using this typing. And this is like really, really good practice. And this like both these things together kind of solve a lot of problems together and in a really elegant way. And this is the only way I think I would handle environment variables in a Node.js application. So the last part of this, the live coding session, I would like to talk about the concept of a nominal type system. So TypeScript is laughed at a lot. Rust developers, Go developers, they love making fun of TypeScript. And they are right. They make fun of TypeScript for being weakly typed, stringly typed, and they make fun of TypeScript for being duck typed. So what does duck typing means? In TypeScript, if something looks like a duck and it sounds like a duck, then it's a duck. Even if, so let's have a type of a duck that has wings and it quacks. And even if we have another type of a goose that does exactly the same thing, a goose looks like a duck and it sounds like a duck, so it's a duck. For TypeScript, these two types are completely equal and interchangeable. So even if I have a const of a duck that is of type duck, that has like 2 wings, thank God, and it does quacks, then even if I have a function, for example, that true, so even if I have a function that accepts a goose, for example, let's have a getGoose function that would accept a goose as an argument, this function would happily accept a duck, okay? Because for TypeScript, these two are completely interchangeable. There is no difference. This is the idea of duck typing. So it's about structure. If two types have the same structure, they are the same. And in many cases, like it's true. In many cases, I hope your laptop's fine. In most cases, it is interchangeable, but not always. When? When do we not want things with the same structure to be equal? I will tell you. What if I have an ID that is a string, and I have an email that is also a string? Do I want these two things to be interchangeable? And this is why they say that TypeScript is stringly typed. Okay? All the strings are the same. All the numbers are the same. Primitives are basically like the biggest hardship, I would say. So I wouldn't want, like, if I have an ID, let's say that it's like 1, 2, 3, and if I have a function that sends email, that accepts an email, I wouldn't want it to be able to accept an ID. Like, a Rust developer would really make fun of me for having to deal with these things. So how do we deal with it? What do we do? The solution for this is nominal typing. And if you look in the TypeScript documentation, you're going to see something like this. that I don't really agree with. Okay. So, and don't really agree with this, but this is like the most simple approach for this problem. So it would be looking something like this. So this is what you see in the TypeScript documentation. They add this branding, which is not like a reserved word. It's just a convention. And as you can see now, I'm getting an error. First I'm getting an error here because I can't, ID doesn't comply to this constraint. So I would have to do this. And this is already interesting because this is still a string, but the type is extended. So this brand only exists in the type space. It doesn't really exist in the value space. I can do extra branding on types even without the runtime space. And here now I can see that I can't accept an ID because an ID and an email don't comply. This is the most basic way to solve this problem, but we're gonna start leveraging it up. So what we're gonna do is first we're gonna use Zod to do some nominal type system or branding. So what we're gonna do is that we're gonna write a schema for an ID. Okay, so we're gonna say an ID schema is basically. So Zod has, besides strings and numbers, it also has a lot of really cool validations that are beyond the basics. So we can do like a UUID check. We're going to do UUID 7, which is my favorite UUID. And we're going to brand it as an ID. And we're going to do the same thing for an email. So we're going to say that an email schema is an email. And as you can see, you can have like emoji, you can have regex, you can have a lot of things. But we're going to say it's an email and brand it as an email. And then we're going to do the same thing. We'll say that this is an inference of the ID schema like we've seen before. This is not really interesting. But what is interesting is to see the following thing. So we get an error. We got what we wanted. And what is the way now? Like, how can I say that something is a valid email? So in fact, there's only one way to type something as an email from now on, since the email is branded, and it's to go through the email schema. So if I go through the email schema, then anything that goes through it is typed as an email. So it's really cool because it kind of like completed this circle, because I have a runtime validation, and out of this runtime validation, I created a type that would require runtime validation, because my only way to type something as an email now is to go through my email schema. So this really gives us a lot of extra safety, but it's still not enough. In fact, what I showed you now is not really a nominal type system. It's just fancy duck typing. Why am I saying that? Because let's go back to before parsing it. So I have this error, okay? I can say that this is like an ID. I can't say that this is an ID. I have to go through and say that it's an ID schema that parses this, and then it's an ID. And the problem is, and why do I say that this is fancy duck typing? Because if somewhere else in the code base, two people gave brands the same name. So this is now, let's say that I brand this as an email. Okay, I give this the same brand. And now it works. So even though I have different validations, they are different types, but they have the same structure of a string that's branded as an email. So it works. This is not a nominal type system. But there is one way to turn this into a nominal type system and to make TypeScript a strongly typed language. And it would be with using my favorite primitive, a symbol. So if we create an email brand that is a symbol of an email, a symbol is a primitive, but it's a special primitive because it has a reference. So we could do, instead of typing here, this is also a symbol, by the way, but this is a symbol that has a reference that is consistent. So if I give this the email brand, and other way around. So if I give this the ID brand and I give this the email brand, so this doesn't work. But even if they would have the same, the symbol is created of this, it's the same symbol, right? Like it's an ID, it would still not work because these are not the equal, okay? Even though they are the same symbol, they have different references. So if, for example, I create this schema validation, and I export only the schema and the type, but I wouldn't export this symbol, there would be no other way to go through this email type, like to type something as an email without going through this specific schema. I'm literally creating a unified source of truth throughout my whole code base, and there is actually no other way to do this besides using symbols and nominal type system. And it's cool for like really big systems when you do want to make sure that you own the validation for the type that you expose. And I think that this is enough, at least live coding for me at 9:30 a.m. And I would like, for the rest of this talk, to focus on the future. So I said at the beginning of this talk that this has been a really, really exciting year for TypeScript enthusiasts, that we got a really, really exciting message from the TypeScript team last March, that by the end of this year, we can expect to get a major version of TypeScript that's going to be 10 times faster. I'm just curious, like, raise your hand if you heard about this. Okay, good. Just curious. So TypeScript is going to be 10 times faster because they did a really, really big project for the past year in which they ported TypeScript to Go. So first of all, we're going to start, before we talk about what porting really means and why Go, we're going to go to the TypeScript repository. So this is the TypeScript source code, okay, as we can see. And when we're going to go down to see what languages can we find in the TypeScript repo. So TypeScript is written in TypeScript. For somebody that doesn't, if somebody doesn't deal a lot with compilers and stuff, it might seem weird. But as a matter of fact, this is common practice to write compilers in the same language. This is what's called a self-hosted language. There are a few really good arguments for writing a compiler in the same language. The first argument is a product argument. So if I am a developer of the TypeScript language and I write my compiler in TypeScript, I get a really solid understanding of, I am my user. I understand what features are lacking. I understand the experience of my users, rather than when you're coding in a different, you're creating a language in a different language and you don't even know what your users feel. So this is like the primary reason, which is product-wise. But another reason, which is more TypeScript specific, is that when TypeScript started off, so that was 2012, and at the time, editors' IDEs weren't as advanced as they were today, and they really wanted to make sure that TypeScript can run anywhere that JavaScript can run. So the only way to do that was to write the compiler in JavaScript, which is, so they write the compiler in TypeScript, and eventually the compiler runs in JavaScript. Now, you remember how much you had a bad time when I showed you how type checking really works under the hood in a really, really cute two-liner? So that was a two-liner. What if we have like hundreds of lines? What if we have dozens of files with hundreds of lines? What if we have hundreds of files with thousands of lines? This is the reality of a lot of code bases. You remember how many hops it took us to do a two-liner? What happens in a code base like this? There are code bases like this. And this whole thing is run with JavaScript. JavaScript is great. It's, to say the least, not intended to do all of the things that it does today. It's not like a wolf. It's more like a sheep with a gun. And by this point, like, the decision to write TypeScript in TypeScript was it was a solid decision at the time. But we're starting to see the end of it when we see performance of very, very large projects with like millions of lines of code, and build time and editor startup time it's becoming a bad experience. And if TypeScript gives people a bad developer experience, then we're completely losing the point. And you might be thinking to yourself, but JavaScript, like you can do multi-threading in JavaScript, like JavaScript can be efficient, and like JavaScript does support multi-threading, like in Node, but it has really, really limited support for shared memory between, like shared memory concurrency. So like you can do multi-threading, but the memory they share can only be bytes. So anything that you want to share between threads in JavaScript, you have to marshal it into bytes, onwards and backwards, which is really not efficient for something this big when you want to share this memory between different threads and to like make this process happen in parallel. JavaScript can't really help you out with that. So performance is getting really bad, and this brings me to the words of Anders Hallsberg, which is the creator of TypeScript. So the core value proposition of TypeScript is an excellent developer experience, and as your code base grows, so does the value of TypeScript itself. But in many cases, TypeScript has not been able to scale up to the very largest code bases, and developers working in large projects can experience long load and check times, and have to choose between a reasonable editor startup time or getting a complete view of their source code. So we're starting to see we're seeing the end of when the decision to write TypeScript in TypeScript was good. JavaScript is not really a language that's built for processing really, really big loads of data. And it's also not a native language. Like even with V8 isolates, like even though like just-in-time compiler makes it slightly better, but it's still not a native language. And you can see that after the porting, the performance improved by 10, which is really, really impressive. So what they said is that they gained 40% of the improvement just from going to a native language, like just from doing the process, not even parallelizing it. Just going to Go already made it 40% faster. And the rest of the 60% of the velocity was thanks to concurrency. And I'm reaching the last words of Anders, which we've probably reached the limit of what we can squeeze out of JavaScript. And what I did not answer now, and I just realized, is why Go? Like, how did they end up with Go? And the truth is that they did a lot of research between different languages, which was quite impressive as well. So they looked out at Rust, they looked at C#, and they ended up with Go because what they were looking for was the language that was the most similar to TypeScript, so they could automate a lot of the process of the porting, because they didn't do a migration. They didn't refactor TypeScript. They really wanted the same code base, same names, same functions, same structure in a different language. That's the meaning of porting. So they wanted to find the language in which they could port to in an automatic way. And it's really quite impressive because within 1 year, they ported the code base that they've been building for 10 years. And that's possible also thanks to the research and to AI and to advanced automations. But it's also possible because the TypeScript code base has 120,000 test suites. So if you feel bad about the tests in your organization, you can feel even worse now. So thanks to you for listening to me talk about TypeScript at 9 a.m. for so long. If anybody wants to connect, this is a QR code. And also, if anybody has questions, ask out. And thank you. Thank you. Somebody else?